everybody. Hey, I'm getting more and more familiar with Cauchy Schwarz. And Cauchy Schwarz, the Cauchy Schwarz result is this guy right here, just called the CS, Cauchy Schwarz inequality. And it is an inequality that holds for any sequence A sub I, B sub I. It can be positive, negative. There's no constraints. They can be complex numbers, real numbers. You're not confined by saying all positive reals or anything like that. Now, we have some initial conditions here. It turns out all the K sub i's are positive. They sum to 1. So you got n of them. They all sum to 1. All right. And we're supposed to show that the summation of the reciprocals is greater than or equal to n squared. Another way of saying that is the sum of the reciprocals is greater than or equal to the number of summands squared. So you have n summands here, and the number of summands is connected to this. All right. Now, this alarmingly simple fact right here is what we actually use. And we actually will use this guy right here as far as the notation goes. This will be behaving like the A sub I. Yeah, that'll be the A sub I right there, sorry. And then this will be your B sub I right here. Now, I know that's kind of clumsy, but for me, I'm not going to write it down every time, but it's kind of a good idea. So this object right here is your A sub I. This object right here is your B sub I, and this is just the reciprocal property. 1 is equal to this. It's crazy how simple some of these substitutions are. Okay. Now, so what we do right here is this is just a straight substitute. If you look at your A sub i's here, and also notice that for our case, n is certainly equal to 3, right? Or is it? No, never mind. N is just, n is, we'll be doing that later on, but n is unbounded here, okay? Now, so anyway, y'all, again, with these choice of substitutions for A sub I, B sub I, you just take off. In other words, this is just a direct substitution of this Cauchy Schwarz inequality. And so here we go. I mean, there it is. You can see it. There's no need for me to read it. And again, it's just a straight substitution using A sub I, B sub I, these choices in this Cauchy Schwarz inequality. Okay, so there it is. Everything lines up. Squared, squared, right? Squared, 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 right? Okay, very mechanical. Now, so what happens right here? Well, this piece right here is squared, so it certainly becomes the K sub I, summation K sub I. But notice this piece right here is given to be 1. Okay, so this circled object right here is just equal to 1. Okay, all right, and then right here, we're just exploiting the fact when we square these guys, we're just summing up a bunch of 1s, right? But almost by definition, the summation I equals 1 to n of 1 is just n, right? So this is just n squared, right? Notice that 1 is unindexed here. So you're just adding 1 up n times, right? So for example, if n were 4, you would be adding up 1 4 times, which is the same as 4. So you get n squared right here. So the result follows. Everything is good. Right here, the summation 1s, well, yeah, I just wrote it down again right here. And then I just removed this piece to get the final result. Okay, so hope that helps. And also, let's work with a concrete example. And before I do that, I want to talk about, there's a gentleman by the name of Goldmacher who came up with this really great mnemonic for this, for the Cauchy Schwarz. If you're having a hard time remembering the Cauchy Schwarz, this says the product of the sum of the squares is greater than or equal to the sum of the products squared. Isn't that neat? You just kind of reverse product and sum again. The product of each of the sums squared is greater than or equal to the sum of the product squared. You see, it has a nice linguistic ring to it. So that helps me to kind of remember the structure of Cauchy Schwarz. Now let's work with a concrete example. Let's try n equals 3 here. Okay, just to check this out for concrete, something concrete. So let's try n equals 3. All right. And of course, that will imply that n squared is 9, right? If n is 3, n times n or n squared is equal to 9. All right, so we'll just write that down, word get go here. Okay, now let's just pick some numbers that work. I'll just make up some numbers here. Why don't we try 1/6? And let's just write this. I'll just write it down as we go. So I'm going to do, well, okay, we'll just write down our values. We'll write down 1/6. Okay. I'm trying to, yeah, 1/6 plus 1/3. Plus 1/2. Now it's not hard to verify that 1/6 plus 1/3 plus 1/2 adds up to 1. Okay, so that would be 1/6 plus 2/6 plus 3/6 is 6/6 equals 1, right? Okay, now let's check and see how this works out. So 1/1/6 right here, folks, 1/1/6, okay, would just be 6, right? Y'all, I am leaving out a step right here, but 1/1/6 is 6, 1/1/3 is 3. And then 1/1/2 is 2, right? So that's equal to 11. 6 plus 3 plus 2 is 11. We can do that without a calculator, right? All right, and again, y'all, this is a statement right here of 1/k sub I, 1/k sub I. Each one of these is your 1/k sub I. In other words, this guy right here is 1/1/6, right? Okay, this guy right here is 1/1/3. And finally, 1/1/2, right? Which sum up to 11, which is greater than 9, right? 11, this 11 we got right here is certainly a larger number than 9. So we did check it out for at least one special case. Now this is something you could do directly, but just think if you had a probability distribution where you had like 100 of these guys, you know, it would be a pain to do this directly, but you would always know that you would have this lower bound of n squared. Hope that helped. Hope you liked it. Let me know.